What's another motivation for ABMs? What else might they allow us to keep track of that'd be useful? Well, it turns out as heterogeneity rises, the number of types of distinctions we want to make between people. As we go from making a distinction purely based on susceptibility to one illness. Imagine if we wanted to keep track, okay, the number of times people spend a factor. That blows up the model. How if we have to keep track of males and females? What would we need to do? Copy the model once for males, once for females. How if we want to keep track of 17 age categories? Sorry? Yeah, 17 other columns, one for each age, and then we'd have progression among those age categories. Okay. Suppose we want to keep track of breakdown by people's income levels. Well, suppose we want to keep track of 10 different income levels. We could copy it 10 times. But it starts to blow up, right? Consider 2 ethnicities, 2 genders, 17 age categories, that's 2. It blows up by a factor of 2 times 2, right? That's 4 times 17, right? 68, factor of 68 times. Now, it turns out that if you just have a couple categories, it's not that bad. So it turns out Benson, not your particular version, but a version that is available to any student in this class, if you just ask. It's a licensed version. It allows you to actually have subscripts associated with each stop. So you can have susceptible subscripted by, call it S, subscripted by age, by gender, by ethnicity. And you can do that quite compactly. But it starts to get quite awkward because you have to start thinking about the flows from each one of these states to the others. It also blows up very quickly the size of the model. And if you start to go from 3 to 4 to 5 to 6 of these distinctions, at some point Benson says, I can't do it anymore. And it's a small number. Okay. So it turns out that heterogeneity is captured much more cleanly within an individual level model. For each individual, you keep track of their attributes. So let me ask this: if we were to double the size of this aggregate model, if we were to go from this with males, this with one population to this with males and females, how would that affect the running time of this model? It would double it. No, twice as many stops. If I were to add a variable indicating gender to each agent, how much does that change the running time? Sorry? For an agent? Not necessarily. In an agent base, no. It wouldn't wouldn't change it typically. I mean, okay, if you inserted a lot of rules that depended on that, maybe, but just inserting the attribute doesn't double it. It actually doesn't double its size either, certainly. How if I double the population size of this model? So it's no longer 1,000 people, but 1,000,000 people. Does that bring my computer to its knees with this sort of aggregate model? How does it change the time? Doesn't at all. These are just different numbers. Just a different number in here. It's just multiplying numbers that are larger or smaller. And it has essentially no impact. How about an agent-based model? If I double the population, does that change our running time of an age-based model? Yeah, it at least doubles it. Sorry? Often it's worse than doubling. Why could it be worse than doubling?
What happens in the different relationships between agents that's tracked.
That's right. So networks between people, for example, might connect up a large fraction of the population into change, and then you have some scaling that goes up. The number of network connections may go up more than linearly with the number of people in the population. There's another reason though, and it has to do with computer hardware. And those from computer science background, this may not jive with you, or it may not resonate with you. But it turns out that you know, at some point as we grow our memory constraints, or the amount of memory required by a model, the speed of the model decreases very rapidly. That information has to be put on disk, which is much, much slower than having it on memory. And so it will really, really slow it down. So it turns out that doubling the size of an agent-based model will typically somewhat more than double, and sometimes drastically more than double the running time. Here, it's essentially no difference. So with heterogeneity, with differences between the people, it turns out it's much easier to keep track of that in agent-based model. And I'll highlight this, folks. Well, suppose this. Riddle me this. If I wanted to keep track of each person in this population by their birth weight, I want to represent their birth weight. What was their weight when they were born? How would I do that? Sorry? If I wanted to keep track, so here's this population, susceptible, infected, recovered. I want to keep track of it. I want to keep track for each person what their birth weight was, because I want to see. This may sound weird that's all, for a spread of an infection, but it turns out for certain types of conditions, like diabetes and so on, your birth weight may have an impact some on your later life experience. So if I wanted to keep track of their birth weight, how would I do that? Okay, right. So I discretize it. I turn it into a set of categories. Turns out that that's not required in an agent-based model, an individual level model. We could just keep track of their birth rate. Their birth rate is 1.5, you know, 1.5 kilograms. It would be, you know, 3 kilograms is their birth rate, 3.5 kilograms, or 3 point, you know, however much detail you want to put, that's fine. You don't have to discretize it. You don't have to turn it to categories. Now, those are some of the reasons. It turns out that there's some additional components. If we want to understand network structure, we want to see how an infection is spreading over a network, or how someone's social networks, the people they're connected to by proximity, or people they're connected to socially, how does that affect a person? Doing so within a network like this is much easier to do in an agent-based model, an individual level model. Similarly, if we want to keep track of someone's situation in space, we want to keep track of their location within a hospital, or their location over some region of space. They're wandering within the Saskatchewan landscape. To try to do that within an aggregate model, we might be able to keep track of spatial location, but what will we do? By the same token, we would subdivide those categories, those stocks, copy it for each sort of square. Within each grid point, we could create a copy of the model. But here, we can have the agents, and that might be very sparse, by the way. But here we can have the agents each keep track of their location and be displayed on a network and interact with the environment and so on. So that has some advantages there. We talked about sort of multiple levels of scale. And it's worth noting that in terms of the dynamics, if we're interested in spatial dynamics, this sort of pattern, or this sort of pattern, we can examine that rather more easily within an agent-based model. We could also look at these so-called reference modes we talked about with aggregate models in an agent-based model. We can always aggregate up across the entire space, count the number of susceptible infections recovered, and plot it out over time. And this gives us something, the sort of plot that we were getting in Vensim earlier with an aggregate model, right? The number of infectives over time. We could look at that, couldn't we, from this? It doesn't rule it out, but it lets us additionally look at patterns on that landscape, for example, or patterns within a network like this. Okay, so these are very crudely some motivations, and I talked about multi-scale models. So here we see emergent behavior that comes out of both. I should really be careful with my categories here. This is system dynamics. I'm talking aggregate and individual level model. In a system dynamics model in general, in an aggregate model, you see the emergent behavior coming out of interactions of stocks and flows. The stocks and flows interact in complex ways. We saw that before, nonlinearity, right? S times I over S plus I plus R times C times beta. The fact that we had a nonlinear term there let it act in sort of unusual, sometimes surprising ways. The effects could die out under some values of C, and it could explode under others. So we see that in system dynamics, these interactions. Agent-based models, a lot of the dynamics are occurring between individuals, individual to individual. There's some within an individual, but there's a lot kind of between those individuals, and sometimes individuals in their environment as well. An agent-based model in particular emphasizes multi-level emergence, how this emergence comes out of multiple levels of a hierarchy. So there's emergence, which occurs at the level of individual behavior, then at the level of a city, and then at the level, say, of a region, which might be quite different. So we have some real trade-offs between these types of modeling. And in fact, the types of modeling can be used together quite well because they're complementary. It turns out aggregate models of the sort we've been looking at are somewhat easier to construct. They don't require programming in a sort of a classic sense of the term. We're not writing for loops, in a traditional sense within our aggregate models. We're not declaring variables in Vensim in a textual sense. Later we'll talk about it's a declarative language of sorts, but it's not. It doesn't raise the same sort of programming challenges that you'll sometimes see typically see in the agent-based side. And it turns out aggregate models, we know how to formally analyze them. We just can describe them as differential equations. We can put them up there, and we can go ahead and sort of analyze them using formal theory from applied math. So for those for whom this is meaningful comments, we can use eigenvalues and look at the eigenvalues. Those analyses that I talked about, which sort of identify what are the dominant loops at one point in time, which loop is dominating right now, which is it a balancing loop or the reinforcing loop, that's based on formal analysis. And you can't really do that. We don't know how to do that with an agent-based model. We don't have the tools for knowing how to do that effectively. Turns out aggregate models would typically be quite a bit faster. They slow down a lot as you add in heterogeneity, but they often run quite a lot faster for large populations than an individual-based model. And the fact that you can build them more quickly often means you have more time to understand them and refine them. An individual-based model, though, has a lot of benefits to it. It can provide better fidelity to certain types of dynamics. It can allow you to represent really targeted policies. You can say, I want to target people who are in highly connected cities, or I want to target that subset of people who have more than 6 neighbors here. Or I want to target people, deer that live on this island, or something like that. We can really simulate things that are very, very specific often. And we can make use of people's, what I call longitudinal data. So biographical information about a person. We might treat them differently. If they've been infected more than twice before, we do something different with them. We give them a different drug, or we take them for counseling, or we keep them longer, or what have you. And you could use that information about how long it is between times people get infected to compare to actual historical data you have at the level of an individual. Within an aggregate model, we don't really have that option. We can't really formulate in general statistics on how well it matches historical data at an individual level. In an aggregate model, we can't really say, is it the same individual who's here in the susceptible stock again who was here before? We don't have a way of answering a lot of those questions. It's just a count of individuals. Is it the same one? Is it a different one? It's a count of individuals. It's considered, the fact that they're in that susceptible stock, it's considered to summarize all the information about their history that we need to know. So we can't really ask, is it the same person who was here a month ago? Can't ask that. Whereas an individual-based model, you can. If we're interested in understanding how an intervention affects people with certain characteristics, who live in certain regions more, from certain ethnicities or certain age groups, we can often do so more easily in an individual-based model. Often individual-based models will be somewhat more convenient, somewhat more flexible in representing things. Ladies and gentlemen, do you remember, at the cost of kind of rewinding this, do you remember when I said, how is it that if we have this model, susceptible, infected, recovered, how would we keep track of people by ethnicity, different ethnicities, or by different genders? What would we do? We copy it, right? So suddenly, if I want to explore representing a certain type of heterogeneity, keeping track of people's income, I want to explore that. Maybe I want to keep track of people's gender or something, just on an exploratory basis. Now I have to modify the structure of the model. I have to actually, globally, across the whole model for people being represented by this population, I have to copy it, duplicate it. Maybe later I decide, well, I don't need to keep track of gender. Now I have to go back across the entire model. If I put in gender as an attribute of a person in an agent-based model, does that require me to change everything in the model? All the rules? No. I could put in an extra rule about what to do with gender, but it doesn't require it. So in terms of flexibility for representing additional factors, you can get some benefit out of an individual-based model. A similar thing is, I asked, what would it take to represent waning community like we did in the agent-based model. In both cases, we could just add a flow here or a transition in that model you built up. But if we wanted to keep track of how many times they got infected, here we're talking about copying the model. So here we're talking about needing to modify model structure just to keep track of a piece of information. Whereas in an agent-based model, you can often just add in an extra variable and keep track of it quite straightforwardly. So there's some distinctions there that are worth bearing in mind. Okay, so just going back to this, and then sometimes if we understand things at an individual level, if that's how we kind of understand how things work, often characterizing it in an agent-based level or an individual level characterization is easier. We don't have to write out that S times I over S plus I plus I. We don't have to go through that. We just say, well, people are in networks, and when people are in a network, if I sneeze, Kurt may catch it. I'll spell right. If I sneeze, Kurt may get it when he's visiting me in my office. And so we're characterizing things kind of at a level we might be more familiar with, whereas someone with more mathematical background, it would take maybe someone with more mathematical background to be comfortable with the S times I over S plus I plus R, etc. So there's some trade-offs here. Now, what I want to emphasize is that both of these have advantages in different areas. And it turns out that there will be some cases where the individual-based models really make sense to do. There'll be some cases where our knowledge or data availability or other things are such, or the amount of time we have, the skill sets available, that an aggregate model be appropriate. And we will see soon enough how we use stock and flow models within agent-based models. So we'll have agents and their behavior is partially described by stocks, flows within a stock associated with their level of blood sugar or their level of the amount of fat versus non-fat in their body or what have you. So there we can have dynamics described by a hybrid sort of model. Anyway, so this is aggregate models and agent-based models. And I provided some key needs here for both of them, okay? I wanted to, yeah, and then there's some sort of limitations here which are significant we'll be dealing with. We'll maybe talk about the elephant later. Okay, I wanted though to emphasize one thing. We talked about system dynamics dealing with feedbacks as the focus of system dynamics. Where do feedbacks come in an agent-based model? So suppose we have a situation where we're modeling in a system dynamics model someone's nicotine exposure and the way it addicts them to cigarettes. So, you know, someone has a certain likelihood of smoking, and through smoking they get exposed to nicotine, they get more nicotine exposure, that leads them to be more addicted, and they're more likely to smoke. This is kind of a vicious cycle that gets people smoking. They get hooked to smoking because of this. And an agent-based model that operates as well, right? This is kind of, we could characterize this at an individual level, right? This might be in a system dynamics model, actually, is sort of a representation, and that might operate at an individual level. But there are going to be some things within a system dynamics model in an aggregate level that are not going to be feedbacks at an individual level. So if we have smokers, for example, maybe we say the more smokers there are, the more peer pressure there is to start smoking among kids, and therefore the more likely they are to start smoking, and therefore the more smokers. So this would be a cycle that we might have in an aggregate model. But if you really unpack that at an individual level, that's not a feedback at an individual level. Instead, you know, Johnny's perception of maybe Johnny smokes here, and then he, where I got these pictures, but he you know, offers cigarettes to someone else. And so here we have influence that's captured here in a feedback based on the count of smokers. Here it's not a feedback between individuals directly that's represented here. It's, you know, Johnny affects Timmy, and Timmy's now more likely to smoke. So what's a feedback in an aggregate level might not be a feedback at an individual level. That's just sort of a pointer here.
Is that one of the reasons why it's hard to unpack the math behind it? Because the math that we understand as from aggregate models comes from the positive and negative feedback, basically.
Yeah.
And then from there you can develop your relational equations. But you have to unpack. I mean, you kind of have to look at the model and see the causal relationships and then create the equations from there.
The fact is, so this is a graduate course, and this is one of the things the flipped classroom affords us, the chance to get into a little bit more deeper issues. So some people will characterize the distinction between aggregate models and agent-based. Let me put it more broadly. We don't know what the relevant distinctions are, okay? I personally have the strong impression, from my experience, I believe it's highly likely that the most important distinction is between individual level versus aggregate. Some other people will say the important distinction is between equation-based models on the one hand and code-based models on the other. That's the important distinction. You have models that are based on equations. Give me an example of a model based on equations. Well, system dynamics model is based on equations. Yeah. Good example. Right. System dynamics modeling is based on equations. And they say the relevant distinction is between that and models based on code. Models based on programming code, programming language code. Personally, I totally disagree. And that's my perspective. Partly it's because I'm from programming language background. And what we do with programming languages, we often seek to describe the semantics of programming languages using equations. And so, you know, it's not like code is a different sort of thing. Equations can't describe it, can't touch it. That's just nonsense. I mean, we can use denotational semantics to describe the semantics of statements that are in code. And to say that it's a totally different sort of thing is, I think, just not accurate. I don't think that's the accurate thing. I think it's, Kurt, I just don't think we have the mathematical formalisms, the mathematical ways of specifying what an agent-based model is doing. And so what we have recourse to is the impoverished sort of use of classic programming languages like Java or C++ or whatever number of languages, you know. And those languages are fine. They do the job. They're computationally universal for whom that's something that's meaningful. After all, anything we can describe in one thing we can describe in another. But it turns out that they're not needed for the job. So we end up writing our models in Java when really there's probably much cleaner ways of describing them. The semantics, what behavior we want to see. That's what we're describing with these models. So that model that you were asked to modify in AnyLogic, that has behavior associated with agents, right? That behavior is, thank goodness, and this is the reason I use AnyLogic, a lot of it is abstracted to a language of state charts. There are these states, right? Susceptible and effective are covered, and it captures the semantics associated with that, but you insert little bits of Java code there. And really, I think what we're seeing, Kurt, over the multi-year time frame, it's a multi-decade time frame, is we're seeing a move towards better and better languages to describe agent-based models, but we're not there yet. And so we force people like yourself to be subject to getting some exposure to Java code so you can characterize it. We've come a long way. We're not describing it in assembly language anymore. We're not describing like we did when I started out, when you folks were probably not even born. And we're not describing it in C. We're not describing it in Fortran. Yes, that was used for a lot. MATLAB. We're describing it, I mean, each of those has some strengths, but we're describing it in something that requires us to write a lot less code in AnyLogic. It's a lot less code. AnyLogic probably reduces the amount of code you have to write, characterize an agent-based model by a factor of 5 to 10 times. And that's good, but we're not there yet. So, you know, glimpse of some of my work. I work with Chris Duchin creating better languages for describing these models. And then once you come up with a crisp way of describing it, the problem is it's hard to analyze mathematically a for loop's behavior. Like, I don't know how to do it. You know, in order to do that, I would have to abstract that behavior of the for loop into a mathematical syntax. And we just don't have a good mathematical syntax for describing how agent-based models work. We need one. And it's people like you, the new generation, and like all those in the room who could contribute that. But you don't want me to lock you in here and probably get you to do it, so I won't try to make you do it. But hopefully over the next 10 years, we'll make a lot of progress. And Kurt, mark my words. When you're my age, I suspect strongly we'll be able to mathematically analyze agent-based models. It's a bet. But in any case, it's a wager.
Many scientists mark their words
We're trying.
into
I think. Well, I may. I know, but yeah. I agree. I suspect that will be true. I think eventually we'll have the language for doing so. It's just right now we don't know how to describe it, so we use the language of general programming when we don't need to. We could actually use much crisper languages with clearer semantics. But Java, C, you give me any language, there is a semantics to it that can be described with equations. So it's not like there's no equations there, we're out of mathematics, this is nonsense. We're not outside the realm of mathematics.
We just don't have clean math.
What's that?
We don't have like
We don't have clean
efficient
math. We don't have clean math for doing it. And we need the clean math in order to analyze, to derive an eigenvalue, model's behavior, what have you. Yeah. Well, okay. Okay, moving right along. Yes.
The problem is that interaction of agent
Yeah.
and the environment
Yeah.
is so complicated that we can't
Yeah.
provide some, mathematical, some general mathematical solution to describe them. I think that's the problem. We have this problem in,
Uh-huh.
for example, multi-iris categories. We cannot
With
describe it.
with what?
The multi-iris categories so
Yeah.
intelligent.
Yeah. So, yes and no. I think it's a very interesting discussion. I agree we may not be able, it may not be tractable for analysis. I think we could probably describe it. I'll give an example. So physicists physicists sometimes deal with high-dimensional systems. Kurt back there has dealt with a high-dimensional physics system before. It's called a tokamak. And there are, it involves like an agent-based model, and involves large numbers of particles and so on. And there are languages for trying to characterize larger scale behavior based on individual movement of particles or something. I think the issue is more the analysis side there, because we can describe how the particles move based on their neighborhood and so on, or based on magnetic fields or what have you. But I just don't know that, because of the complexity of the system, I don't know we're going to be able to arrive at crisp analytic results. It may be that we're in the equivalent of trying to analyze with linear systems tools the behavior of nonlinear models, and we just, we can't do anything but simulate it, right? That's a possibility. I readily admit that. But the fact that I do think we could have a mathematical description of how agents behave that's much more crisp than writing a switch statement or writing a for loop or something like that. It's just I don't think we're even there yet. As far as analyzing them, I agree with you. We may not be able to tractably identify high-level mathematical insights by analyzing these things. But I don't know if it's a matter of not being able to describe the system's rules of operation using a specification that's mathematically based. So I'm trying to distinguish. Does that make sense? Yeah.
Particles in physics,
Yeah.
they don't decide to do something
Based on their
behavior
history, or yeah.
So that's
Yeah.
really make the problem very, very simple.
Yeah.
Comparing with, for example, agents like
Yeah.
people.
Yeah.
It's really
Yeah.
difficult.
Yeah. So I'm not totally convinced by myself, but I agree that there is some potential, but I still think, in as much as that you should be able to characterize hypotheses in mathematical terms about behavior using operators that may be different from what we use right now in normal mathematics, but are still have very clear semantics associated with them and are very mathematically understandable. They're amenable to formal reasoning of sorts. Whether you can deduce high-level things from it, I'm just not sure. I would love to talk with you more about this and see if we could come up with a counterexample. Because I agree, I'm not certain. It may be that the world is. What did they say in Hamlet? He said there's one of the characters in Hamlet who says, "The world is far too messy for your neat theories." And he said the person's name. It wasn't Osgood, but it could have been. It's a quote in Hamlet. You can look it up. Okay, so that's good. Okay, so we'll be talking about agent-based models for the next several lectures, and we're going to be going into, let me stop this sort of,